Hello friends, myself Professor Rajendra Baburao Gharse, HOD Electrical Engineering Department, NB Navle Sinhagad College of Engineering Solapur. I am having teaching experience of 9 years. I have completed BE Electrical from Government College of Engineering Karad and MTech from Indian Institute of Science Bangalore. I was All India 7th ranker in the GATE examination with a percentile of 99.96. So in my last video, we have discussed about the operation and the waveforms of single phase half bridge inverter with RL load. Okay. Today we are going to discuss about the Fourier series analysis of the waveforms of, that is, a V0 low voltage and the load current waveforms of single phase half bridge inverter with RL load, Fourier series analysis. Okay, so recall the waveforms of V0 and I0 for RL load. Okay, so these are the waveforms, right? So we have discussed V0, that is a load voltage waveform, is a square wave. Load voltage waveform is a square wave, and I0 waveform is a triangular wave, right? So this is the I0 waveform, this one is a V0 waveform, right? So if you check this V0 waveform and the V0 waveform for the purely resistive load, okay, whether these two waveforms are same? Yes. And in the case of purely resistive load, we have already done the Fourier series analysis of this square waveform, right? This square waveform, the magnitude is same, the pulse magnitude is of EDC by 2 only in the purely resistive load as well as in the RL load only, right? So here we can write, yes, as V0 waveform is same as that of the V0 for purely resistive load, right? So that is R load. So we can write the V0 expression which is same as that of the purely resistive load. Okay, so what was the V0 expression? Yes, that waveform, the waveform was consisting of only odd harmonics, right? Means for n is equal to 2, 4, 6, 8, 10, etc., right? The waveform or the resultant output voltage will be 0. The waveform consists of only odd harmonics. So here V0 is equal to summation over n is equal to 1, 3, 5, 7, 9 up to the infinity 2 EDC by n pi into sine of n omega t. We have already derived this expression for single phase half bridge inverter with purely resistive load, the V0 waveform in that case and the V0 waveform in a RL load. Yes, the V0 waveform is same, right? These two waveforms are same. So that's why the Fourier series analysis for that waveform, again it will be a same, right? Again it will be a same, right? Next, in the case of purely resistive load, what was the expression for I0? Yes, in the I0 case it was like summation same, n is equal to 1, 3, 5, 7 up to the infinity. It was 2 EDC by n pi r. It was there, it was only purely resistive load. That's why it was only 2 EDC by n pi r into sine of n omega t. But now the load is RL load, right? And the load is RL load means, as we know, the inductor is having reactance, right? Inductor is having a reactance. So what is the inductive reactance? XL, it is a omega L. But whether the omega, that is a angular frequency, for all the harmonics it will be same? No, right? For fundamental it is, for third harmonic the frequency is 3 omega, for fifth harmonic the frequency is 5 omega. Similarly for the nth harmonic, what is the frequency? Definitely it will be n omega. So therefore the inductive reactance, that is the opposition offered by the inductor to alternating current, right, or to the nth harmonic current, it will be changing depending on the frequency, right? As the frequency increases, as the order of harmonic increases, definitely its frequency increases. So whatever the opposition offered by the inductor to that current, definitely it will be increasing, right? So there is a change in the expression, right? So I0 is equal to, instead of r, now we are having 2 EDC by n pi, instead of r we are having under root r square plus n omega L bracket square. So please be careful, try to understand it. It is like V by Z. What is a Zn? It is a Zn. For n is equal to 1, it is a 1 into omega L. For n is equal to 3, it is 3 into omega L, right? Why this inductive reactance is changing? Because the frequency of all the harmonics is not same. As the order of harmonic increases, definitely its frequency increases, right? Because next, so sine of n omega t minus theta n. In the purely resistive load, it was only sine of n omega t, but in the RL load, it is a minus theta n. Why it is a minus theta n? Because as we know, in the case of RL load, the current flowing through the load lags the voltage across the load by angle, some angle theta, right? So here this minus angle indicates this is a lagging, right? And the theta n is the lagging angle of yes nth harmonic, right? Nth harmonic. So where theta n is equal to tan inverse of n omega L by R, and this term under root R square plus n omega L bracket square is nothing but the Zn, right? Zn means the opposition offered by circuit to nth harmonic current, right? Zn is the opposition offered by, or the impedance offered by circuit to the nth harmonic current, right? So for the fundamental, yes, it will be having some lesser opposition, that is a Zn. N is equal to means Z1 under root R square plus omega L bracket square. But for third harmonic, it will be Z3 is equal to under root R square plus 3 omega L bracket square. So impedance will be increasing. For fifth harmonic, it is under root R square plus 5 omega L bracket square, right? Similarly for 7th, 9th, 11th and so on, right? Are you getting the point? Okay. And theta n is the lagging angle between nth harmonic current and nth harmonic voltage, right? Nth harmonic current and nth harmonic voltage lagging angle. So are you getting the point? What is the change? So here we need to consider under root R square plus n omega L bracket square. This is a I0. Next, so fundamental output power, right? Fundamental output power means the output power, that is a load power due to fundamental voltage and fundamental current component, right? That is a V01 generally we say, or we can say E1 also, E1. Okay. So next, let us discuss the expression. Output power at fundamental frequency, that is n is equal to 1, right? So what is a P1 RMS? E1 RMS into I1 RMS into cos of theta 1, right? So instead of theta n, now it is a theta 1. As we know in the AC circuit, what is the power? V into I into cos phi, right? Or the cos theta. Okay. So instead of V, now you are having E1, right? Or V01 you can write into I1 is nothing but I01, okay, into cos theta 1, right? Cos theta 1. So it will be I1 RMS square into R. E1 RMS is RMS value of fundamental output voltage, I1 RMS value of fundamental output current, and theta 1 tan inverse of omega L by R. So from this we can write I1 RMS, yes, it is a E1 RMS or V01 RMS divided by impedance, right? V01 RMS is 2 EDC divided by root 2 pi into yes, impedance is R square plus omega L bracket square. So P1 RMS is I1 square into R. So that's why the expression for the P1 RMS is this one, right? This is the expression for P1 RMS, right? Next. So are you getting the point, right? As long as the load changes from R to the RL load, right, there will be some changes in the expression of load current, right? And here we need to consider the angle of lagging also, Next, so let us discuss one example. A single phase half bridge inverter. The half bridge inverter has a source voltage EDC is equal to 220 volt, right? That is a EDC is given 220 volts. So EDC by 2 is 220 by 2, that is 110. Okay. The inverter supplies RL load with R is equal to 10 ohm and L is equal to 10 millihenry. The inverter frequency very important because this frequency is required for finding the value of omega, right? 400 hertz. Okay. Calculate RMS load current at fundamental frequency, that is a I1 RMS किंवा or I01 RMS or I01 RMS. Next, RMS value of load current, that is a I0 RMS. I01 RMS is this one, this is I0 RMS, and output power, that is a P0. Output power means total output power, right? So I01 RMS, it is, yes, we have already derived 2 EDC by pi under root r square plus omega L bracket square into sine of omega t minus theta 1, right? For the fundamental it is 2 EDC by pi, because it was 2 EDC by n pi under root r square plus n omega L bracket square, right? So from this it is 2 EDC by pi under root r square plus omega L bracket square into sine of omega t minus theta 1, right? Now from this, what is omega? 2 pi f. So it is 2 pi into 400 into 800 pi radian per second. Okay, so this is a I01 RMS. After putting the values, we can write it as I01 RMS is I01 peak divided by root 2. Okay, so I01 peak is this value divided by root 2. Okay, so this term, and finally we can get the answer after putting this. It is 3.66 ampere. Are you getting the point? What is this I01 peak? I01 peak is nothing but, this is a fundamental current, right? So sine, it is a sinusoidal term, so can we say that this is a peak value? Yes, so peak value divided by root 2 is nothing but the RMS value. So this term we have taken to, yes, r square plus omega L bracket square divided by root 2. Okay, so that's why it is 3.66. After calculation it will be 3.66. Next, I0 RMS. I0 RMS is V0 RMS divided by under root r square plus omega L bracket square, right? Because while finding the I0 RMS, we are considering it as a omega L, because it is like a steady state operation, right? Normal calculation of AC circuit. So that's why it is V0 RMS by under root r square plus omega L bracket square. What is a V0 RMS? We are having a square wave. So what is RMS value? It is a EDC by 2, right? EDC by 2, and after putting the values you will get, so I0 RMS 4.068 ampere. Next, output power. Yes, output power is V0 RMS into I0 RMS into cos of theta, or this can be calculated as I0 RMS square. In both the ways you will get the same answer, right? So V0 RMS into I0 RMS into cos of theta. Again, theta is tan inverse of omega L by r, right? So it is 165.45 watt, right? So this is about the single phase half bridge inverter with RL load, right? Fourier series analysis we have discussed, and one numerical we have studied, right? Next, so points to be remembered, points to remember. Yes, for the single phase half bridge inverter purely resistive load V0 waveform and the V0 waveform in single phase half bridge inverter in RL load, in both the cases the V0 waveform is same, right? V0 waveform is same in both the cases, right? Next, so whatever the Fourier series expression of V0 waveform in purely resistive load, that will be copied case of RL load V0 waveform, right? But I0 waveform in the purely resistive load, it was like V0 divided by R simply, but here instead of R we are having R plus J into omega L actually, right?